Hello. Hello, everyone. Good to see everyone. Hello, Toby.
Hello.
All right. Happy New Year. Toby, I can see that you're logged in twice. Which one of you should I make the host?
The one, I don't know if you can see which one is currently talking, but the
The
other
ones that
one.
are currently talking. Okay, that's
As
the
in,
one.
I think they're connected. So if you make either one host,
Okay.
it works.
Right.
But I think the one that's not talking,
Oh,
because
the one
that's the
that's
one I'm
not
going to
talk.
share screen in.
Okay, then. Okay, I've changed. So the one that's talking now is the host. So you can see now. You can change the host. It should be fine. You should be able to reclaim the host or something.
Yes, I think I've done this. I think
Okay,
that's
perfect.
worked.
Excellent. Right. So yes, it's I'll leave it to you and have a great session.
All right, thank you.
Welcome.
Okay, I'll probably start slowly. I know it's the new year, so people might take a little bit of time. Don't know how many people we're expecting, so.
I had fewer than normal on Tuesday, so we might have it might be just it, but people do watch it later because we are recording.
Okay, yes. Okay. Yes, we can all see this, I hope. Okay, so today we're going to be going through electromagnetic induction. So what that is where you have a changing magnetic field in a magnetic field or that changes in any way. What this does is it creates, well, in one sense, it creates an electric field that loops around it. But at this level, what's important is if you have a loop of wire, and inside that wire, the magnetic field is changing, then this creates a current through that loop. And there's two ways the magnetic field through that loop can be changing. It can either changes into the actual magnetic field strength is changing, or it could be that, say, the loop is changing size. So the loop starts small, only a small amount magnetic field can get through. As the loop grows and grows and grows, more magnetic field can go through. So in that case, a current will also be induced around. So a voltage will be created around the loop and a current will flow around it. So let's write down some equations for this. So the first thing we need is magnetic flux. And this given by the phi, and this is equal to the magnetic field strength times area. So this is magnetic field strength, and this is, well, perpendicular area. Everything will be perpendicular to the field, but it could be the case that if the field were at an angle, then you need to take that into account. So there'll be an extra cos theta in there. But I put it in purple because it's not going to matter. Everything is going to be perpendicular today. And then the voltage, or what's called the electromotive force in this case, but it's essentially just voltage. So the electromotive force slash voltage around a loop. This is given by this curly E. It looks a bit like an epsilon, but it's a calligraphic E. And this is minus the rate of change of flux with respect to time. Now, we're going to talk about the sign later. The sign for now doesn't matter. We're just going to look at magnitudes, but we'll talk about the sign later. For now, the electromotive force is just the rate of change of flux. And as we said, flux can change in two ways. It can either be that the area is changing, so the loop of wire gets bigger or smaller, or it could be the field changes strength. So let's look at an example. So for question 1, a helicopter is flying. Its blades have to rotate 500 times a minute for it to fly. The circle swept out by the blades has a radius of 2 meters, and the component of the Earth's magnetic field into the ground is 50 microteslas. What is the potential difference between the center of the blades and the edge of the blades? Remember, potential difference, voltage, electromotive force, they're all interchangeable. So to work out the flux, we need magnetic field times area. So we need to work out the area swept out by the blades. So if the blade starts here, and then later time it's here, and these were 2 meters. The angle swept out is theta. So theta equals the angular frequency, omega, times the time they've been spinning for. And the angular frequency is equal to 2 pi. We'll do everything in radians. It makes everything much easier. So it's 2 pi, so the total number of radians in a full circle, divided by the time period, times the amount of time the blades have been spinning for. Okay. The area swept out, this is just an arc. So from geometry, we know that the area is equal to pi r squared, which would be the full area of a circle, times the angle, theta. And this is in degrees, so there's no, sorry, this is in radians. So in degrees, there'd be this divided by 360, but there's not in this case. Sorry, I've written the formula there in degrees. So it should be r squared theta divided by 2 in this case, because we're in radians. The formulas do change slightly. So that's it in radians. And we can put, now we need to sub in for theta. So we have r squared over 2 omega t is equal to r squared over 2 pi over t times the time is equal to pi r squared t over the time period. So this is the area that gets swept out. The flux is magnetic field times the area, which is just equal to b pi r squared t over t. And then finally, to calculate the electromotive force, and remember I said we're going to ignore the signs for now. This is equal to the derivative of flux with time, which becomes b pi squared over the time period. And so we need to put numbers in. So what do we need? We need B equals 50 microteslas, R equals 2 meters. The time period, and we said it's 500 per minute. So the time period is 60 seconds for a minute divided by 500 rotations, which is, I haven't written it down, got my calculator, 60 divided by 500 is 0.12 seconds. Yeah, 10 rotations a second seems kind of reasonable when you think about how fast a helicopter blade goes. So now we put all of these numbers in. We have 50 times 10 to the minus 6 times pi times 2 divided by 0.12 equal to which is equal to 0.005 volts. Are there any questions here? Okay. We will have a look at the next one. So in this case, a metal rod is placed on top of two metal tracks, and the tracks form this parabola shape. So we see that y is equal to the square root of x. Where if x is given in meters. Otherwise, we need another constant in there. And this is placed in a constant magnetic field of field strength B that is perpendicular to the parabola. As I said, we're not going to have to, everything's going to be perpendicular, so we don't have to worry. And from the crosses, the magnetic field is pointing into the page. Then this rod is pulled at a speed v, and what is the induced EMF in the rod? So remember, EMF equals d phi by dt. I said, again, we're going to ignore the sign for now. We'll talk about that in a minute. So the flux is equal to the magnetic field times area. So how do we work out the area? So area, this is a curved shape. We need to, if we think about it, we've got y, x, and the graph is the square root of x. And we want to integrate and find this area here. So the area, well, we want twice that, right? Because it's the same above and below. So we want twice the integral of square root x and after a time t. So let's say at t equals 0, we're here. So we want to go from 0, so from here to this point here, and this point here is vt. Right? Distance is velocity times time. So we integrate that, we get x to the 3 over 2 times 4/3 vt 0, which is equal to 4 over 3 vt to the 3/2. Then we want the flux, which is equal to B times A, which is equal to 4 over 3 B, V to the 3 over 2 T to the 3 over 2. And then we want the electromotive force, which is d phi by dt, which is 4 over 3 b v to the 3 over 2. And then we want to differentiate this t, so we have 3 over 2 t to the half, which becomes 2b v to the 3 over 2 t to the half. Okay, are there any questions at this stage? Okay. What's going on? Okay, so now we've neglected the minus sign above. So now let's talk about it. So firstly, remember from the right-hand rule that if we have a current carrying wire that way, then from the right-hand rule, hopefully this isn't reflected, but if the current's going this way, and we take our right hand, then the magnetic field it creates loops around it like this. So they're the fingers. The current is the thumb. The magnetic field curls round with the fingers. So in this case, it's like this. So this is the magnetic field. And now this is where the minus sign in the electromotive force comes in. So when we have an electromotive force through a wire, this creates a current. And the direction of that current is important. So this is called Lenz's law. The direction of the induced current is such to oppose the change that caused it. Okay. Now that's maybe a bit of a mouthful, maybe not obvious what that sentence means. What it means is if you're pulling the rod and the flux is increasing, well, then the current is going to be induced such as to decrease the magnetic flux. I think if it were increasing the magnetic flux, as say in this example, in example 2, say as we pulled the rod, the current was created such that the magnetic flux was increased even more, then it would induce even more current, which would increase the magnetic flux, and we'd have a growing magnetic field. Instead, what happens is as the flux here increases, the current is in such a direction that the current is in such a direction that it decreases the flux. So here, the magnetic field points into the page. So as we increase, so as we move the rod, the magnetic flux into the page increases. So to counteract that, we want the current to create a magnetic field that points out of the page. And so, in this example, the current is going to be anti-clockwise. That way, the current points upwards out of the page. We'll see more examples. So it might be easier to get your head round. It's a bit of a mouthful, Lenz's law. So we'll take a few examples to see it. But are there any questions at the moment? Okay. I believe this one helps. The maths and geometry here is maybe a little bit easier. But essentially, Lenz's law is the point of this minus sign. That is easier to understand via Lenz's law. So in this case, consider a circular loop of wire. It's got a radius 10 centimeters, and it's got resistance of 25 ohms. It's placed in a magnetic field that is perpendicular to the loop. So the magnetic field is increased. What is the induced current, and in what direction does it flow? So, say the current is current is equal to voltage, which remember was the same thing as EMF, which is EMF divided by resistance. EMF is the rate of change of flux. I'm still not writing the minus sign, just because we're going to work out the direction separately. If you do vector calculus at uni, the minus sign will be important because it will work throughout all the equations. For now, the minus sign is more of a reminder. We're going to kind of ignore it when we do the calculation and work out the direction from Lenz's law. So this is the rate of change of flux. And the flux is equal to the magnetic field times the area. Okay, area equals pi r squared. It's just a circle. It's equal to pi times 10 centimeters, which is 0.1 meter squared, which is equal to 0.01 meters squared. Now, okay, so let's work all this out. So we're going to assume the magnetic field increases linearly, so at a constant rate for those 2 seconds. So d phi by dt is equal to, now area is just a constant, it's just a constant loop. So it's area times the rate of change of the magnetic field. And if it's going at a constant rate, the rate of change is equal to the change in the magnetic field divided by the change in time. So this whole thing is equal to area times, I'll put the numbers in. May as well have to do it at some point. We have 0.031 times the change in the magnetic field, 0.3 Teslas. The change in time is 2 seconds. And so if we put all that in, the electromotive force is 0.031 times 0.3 plus 2 is 0.0047 volts. Then the current is equal to the electromotive force divided by the resistance, which is 0.0047 divided by 25, which is 0.0047, which is 0.00019 amps. And now let's think about which direction does this go in. So the magnetic field is pointing up and it's increasing. So we want to create a magnetic field that points down to cancel it out. So we need a B field that points down to cancel, to oppose, to keep the same wording, the increasing flux. So what direction does this? So we see here, magnetic field points up. We want a magnetic field that points down. So we want a magnetic field that goes this way around the loop, which means we need a current that goes in this direction. So clockwise. We have current is clockwise. Now let's look at part B. Now, well, the current is going to be the same value. It changes the current, or this change. Okay, so as the magnetic field decreases, it's decreasing at the same rate as it increased. So the induced current is going to have the same magnitude. So I has same magnitude as part A. Okay, now what about the direction? So now the magnetic field is decreasing. So even though the magnetic field is pointing upwards, it's decreasing. So the flux is decreasing. So we want to oppose this decreasing flux. So we want a magnetic field that points upwards through the loop. We want to induce the current such that magnetic field goes in this direction so that it increases the flux as the flux is decreased, right? We want to oppose the change. And so, using the right-hand rule, we need a current going in this direction. We need current anti-clockwise. Okay, are there any questions? Okay. Okay, question 4. So, 7 grams of wire is made into a square loop and each side length is 3 centimeters. It has a resistance of 7 ohms. It falls through to the horizontal magnetic field such that this magnetic field increases with height. And it increases such that the magnetic field is equal to 2 times the height we're at. And the loop is dropped such that it just falls. It doesn't twist or anything. Let's just assume it falls flat. What is the steady state speed of the loop? Now, this isn't easy. So, as it falls, the flux decreases, right? Because if we look at how the magnetic field strength varies, magnetic field increases the higher we are. So, as the loop falls, the magnetic field decreases. So the flux through the loop decreases. So, as the flux decreases, this induces a current, which, well, we can either think of it, the direction of this current will either be such as to increase the flux through it, or it has to be such as to slow the rate of falling. They have to be the same. So that way, as it falls, the current is such that there is an upwards force. So do you remember that? If we have a current carrying wire passing through a magnetic field, then there's a force on that wire. So the induced current here is going to be in such a way that overall there's an upwards force on this loop. But I think if there was a downwards force, the loop would be not only pulled down by gravity, but be pulled down by the magnetic field, by the electromagnetic induction. And then it would fall down even faster, which means the rate of change of flux would be more. So it'd be more of a force down. So it would fall down even faster, and so on until it just whizzes, goes as fast as it possibly can. And that can't happen. So in order to balance out, the force must be upwards. I mean, Lenz's law is just energy conservation. So, the thing I said was the force of a current carrying wire is equal to the magnetic field strength times the current times the length of the wire. And now, as the current loops around this square, there's going to be, well, the force from the top is going to be different from the force on the bottom. Think, the top wire, the force is going in the opposite direction to the, so the current is going in the opposite direction to the bottom wire. So the forces will be in different directions. But because the field strength is greater at the top, the force at the top must be up, so that the net force is up. So let's call this F1 and this F2. The net force must be up. B is greater at the top of the loop, so it must be that force that pushes up. Net force must be upwards. Okay. Now let's call the top of the loop height h. The bottom of the loop is therefore height h minus L. So the force from the top of the loop is equal to, so F1 equals to 2HIL. I've just substituted in for the field strength. The field strength is 2 times H, remember? And F2 equals 2 H minus L IL, just because the height here is different. Now, the induced EMF we could have worked out these directions all another way. We could have looked at, so it's falling down, so the flux is decreasing. So we need to induce the current such that the flux increases. So that means in order to increase the flux and the flux is into the page, we would need a current going, use a different color, current in this direction. Because that way, these are, hopefully this isn't reflected, but going in that way, it increases the flux. So we're opposing the change. And a current in that direction, so we have a current, again, using the right-hand rule, if we have a current going to the right, a magnetic field into the page, there's a force up. So we could have done it using the right-hand rule, or we could have just noticed that we needed the force to be up, and we didn't have to do the intermediary step of working out the direction of the current. But both ways work. The point is the net force is up, and the forces on the top and the bottom oppose. Now, in order to get the current, we need induced EMF. Now, how do we get this? At each height, it's a different, the field strength is different. So if we draw a loop, here, now at a particular height, let's look at a little thin band between x and x plus dx. So this band has a tiny thickness dx. The magnetic field strength is basically constant all throughout this thin band. So the flux created by this thin band, the small amount of flux is equal to B times L, which is the width, times dx. And remember that B equals 2h. Sorry, well, in this case 2x, because x is our height. Well, dx. Then we add all these up. Now, if we're adding up lots of small strips, lots of small rectangles, that's just an integral. That's just an integral. So we integrate from x equals h minus L, so the bottom of the loop, h minus L, all the way up to h of B times L dx, which is equal to the integral from h minus L to h of 2xl. Now we integrate this dx, integrate this, we end up with x squared L from h minus L to h, which is equal to h squared L minus h minus L squared L, which is L squared times 2h minus L. If you do the algebra, I need to add more space. Okay, there we go. So that's the flux. Now, we want the EMF, which is equal to d phi by dt. Now, which of these quantities here is actually changing? Well, the width of the loop isn't changing. The dimensions of the loop, of the square loop, aren't changing, so L is a constant. But what is changing is the height. So as it falls, the height decreases. So the derivative of flux is 2 L squared dH by dt. Now, we'll go back to the question quickly. What is it that we wanted? We wanted the speed at which it was falling. So I'm going to highlight this because it's dH by dt that we want. So dH by dt is speed we are falling, or the loop is falling. So the current, the electromotive force divided by the resistance, which is L squared over R dH by dt. So we've got all the pieces we need now. We've got or we're nearly there actually. So the total force, one thing we need. At steady state, so if it's moving at a steady speed, all the forces cancel. So the force down, mg, so the force from gravity is equal to the net force from the top of the wire and the bottom of the wire, equals F1 minus F2, equal to, if we zoom up, just scroll up, F1 is this, to H. And then the bottom of it, that's right, F2 was 2 H minus L I L. And we can simplify all of this to be 2I L squared. Okay, underline this and this because that's what we're moving forwards with. Okay. Then remember we wanted dH by dt. So we need to sub in for I. So we have mg equals 2. Now subbing in for I is 2 L squared over R dH by dt. And we have L squared again. Becomes 4 L to the 4 over R dH by dt. Which we can rearrange to get dH by dt equals mg R over 4 L to the 4. And now let's plug in numbers. Well, the mass was 7 grams, which is 0.007 kilograms. G, let's just stick with 10 meters per second squared. Resistance was 25 ohms. Divided by 4 times L is 0, what was it? It was 3 centimeters, which is 0.03 meters. And all of that to the 4. And we end up with, if I've typed everything incorrectly, 5.4 times 10 to the 5 meters per second. So the top speed is really, really fast. Not relativistic, we don't need to worry about anything like that, but it is still moving really fast. Okay, are there any questions about Lenz's law or anything like that. Okay. Okay, so now we want to look at what's called induction. So induction is defined as L, which is the ratio of the flux divided by the current. And now why is this useful? So in circuits, you have something called an inductor. So an inductor looks like this because it's a coil of wire, or quite often in real life. That's a terrible drawing, but it should be neater than that. So you have a coil of wire called a solenoid. And as you pass a current through it, it creates a magnetic field. So there's flux through this coil of wire. The flux through this coil of wire, if the current changes, the flux changes. And so the flux changes, and so there's a voltage induced across the inductor. So in other words, it's a component in the circuit that opposes a change in current. You have a really quick change of current, the inductor creates a really big voltage, and that really big voltage creates a current. So an inductor opposes a change in current in a circuit. So, and we said the electromotive force is equal to d phi by dt, so the rate of change of flux, and that is equal to L times the rate of change of current. So, yeah, so an inductor creates a voltage that opposes a change in current. Something we haven't talked about yet is units, really, for anything. So, let's quickly go back through them. So, magnetic field. This is measured in Teslas. And 1 Tesla is 1 kilogram per second squared per amp. Now, magnetic flux. This is measured in Webers. And 1 Weber is equal to 1 Tesla meter squared, because remember it's field strength times area. And this is equal to 1 kilogram meter squared per second squared per amp. And then finally, we have inductance. Inductance is measured in henries. And 1 henry is equal to 1 Weber amp to the minus 1, because it's flux divided by current. And that is equal to 1 kilogram meters squared, second to the minus 2, amps to the minus 2. So that's the units. Okay. So in the worksheets, you look at and you work out the inductance of a loop of wire, of a solenoid. Today we're going to look at a different type of cable. So the cable works by, there's an inner cylinder of radius A, and we're going to assume everything is just in the outer shell, in the out. So it's hollow. Hollow. Inside. So all of the current is on the outer surface. The inner cylinder is radius A, and the outer cylinder is radius B. And now the way this works is the current goes through the inner wire to some point very far away, loops, then there'll be kind of the edge of the wire, it loops back around, and it goes through the outer surface. So the current, or the total current on the inner surface, equal to the total current on the outer surface. And we want to work out the inductance per unit length. So obviously, the longer this is, the more flux we're going to have going through it. We're going to look at one that's 1 meter long. So unit length, 1 meter long. So let's look at this. So we've got a current traveling in this direction. So the magnetic field is going to loop round in this direction. It's going to loop this way. So the flux, so therefore to look at the flux, we need a surface. And the flux is magnetic field going through a surface, or an imaginary surface usually, and through a loop. But our loop is going to be, here's the top wire, here's the bottom wire, surface is like this. So its length, 1 meter. I want it unit length. So now you have either seen, or you may remember Ampere's law. The magnetic field from a wire is equal to mu naught I over 2 pi r. Have you seen this before? I think you've seen Ampere's law. And so the flux, once again, okay, good, you have seen it, thank you. To work out the flux, we're going to do what we did before. We're going to break it up into lots of rectangles. So let's zoom in on this here. We had the upper surface, B, A, got the inner surface, that wasn't well drawn. And what we're going to do is we're going to split it up into a very thin rectangle with radius. And this rectangle, we're going to start at a distance r from the center. It's going to be dr thick. So the amount of flux, the small amount of flux through this tiny thin rectangle is equal to B, so the magnetic field strength, through that thin rectangle. Remember, it's very thin, it's basically a constant across it. B times the width, which we said was 1, times dr, which, we put that all together, we have mu naught I over 2 pi r dr. Okay, so therefore the total flux through this whole purple surface is equal to the integral. Remember, we're adding up lots of little strips, adding up lots of very small strips is an integral. So we integrate. Now, what's the smallest value? Well, that's the inner surface, which is A. The biggest value is the outer surface, which is B. And the flux for each strip is mu naught I over 2 pi r dr, which, if you integrate, is mu naught I over 2 pi natural log B over A, where, yeah, I think you would have seen this integral before, or something similar enough. So this is the flux through this purple surface. Now, oh, and remember this is per unit length. So the inductance is the flux divided by the current, which is equal to mu naught over 2 pi ln B over A. And recall this is again per unit length. The reason it's per unit length, if you're a very short one of these, then the magnetic fit, then the flux won't be very much. So you're not going to have much flux. If it's really long, you're going to have lots of flux. And if you were to put a long one in a circuit, along one of these coaxial inductors in a circuit, then you'd get a huge change. If you tried to change the current a little bit, you'd get a huge voltage to oppose that change. Are there any questions? Some of these questions have a lot of calculus in, and that kind of can't really be avoided with when you get to electromagnetism, it's very calculus heavy. Okay. This is maybe more of a standard question. So we've got a circuit, and the circuit includes kind of a battery, a resistor, and an inductor. So we're going to look now at what an inductor does. So we're going to use Kirchhoff's law to work out how the voltage changes as we go to work out the voltage and everything. So remember Kirchhoff's law, as we go round a closed loop, then the total voltage adds to 0. So if we go round the loop, we have V. Now the voltage across here drops, so minus IR. And the voltage across here is minus L di by dt. This is another thing where the sign matters, or where that sign is important. So minus L di by dt. And from Kirchhoff's law, voltage round a loop is 0. So what are the initial conditions? So before we close the circuit, we see that there's no current flowing. Therefore, when it's closed, the current must stay 0. Because if it were to suddenly shoot up to infinity, then this inductor would create an infinite voltage. So the current must change gradually. So at t equals 0, I equals 0. So these are our initial conditions. And we've got to solve this integral equation, also this differential equation. So let's get this into a form which you may have seen. So it's going to be L di by dt plus I Ri equals V. Now, in school, you would have seen this as something like a number, I don't know, let's call it alpha, just as a number, dy by dx plus some other number times y equals some other number, c. Right, it's the same kind of differential equation, just different letters. So there are two parts we need. Firstly, let's solve the homogeneous part. The homogeneous part or homogeneous part is L di by dt plus Ri equals 0. We can move this Ri to the other side. So we have di by dt equals minus R over L times I, which we can now divide by I. So we have di I equals minus R over L dt. And then we integrate both sides. So we have ln I equals minus RT L plus a constant. Now, to solve for I, we exponentiate both sides. So in other words, we do e to the power of both sides. So e to the power of ln I equals I equal to e to the power of minus RT over L plus C is equal to e to the power of R minus RT over L times e to the power C. This here, e to the power C, is just a constant. So we can write it as A, which is just another constant, e to the minus RT over L. So we've got the homogeneous part. Now we need the particular integral. Now the particular integral, let's look at the differential equation. We see that the right-hand side is just a constant. So the particular integral is just going to be I equals some constant. We just need to work out what that constant is. So let's put it back in. L times, well, the derivative of a constant is 0. So that first term is 0. Then we have plus RC, the constant, equals V. And this tells us that the constant equals V over R. So now the full solution is I equals V over R plus A e to the minus RT over L. Now, the last thing we need to do is work out A by using our initial conditions. So at T equals 0, I equals 0. So let's put T equals 0, I equals 0 in. We have 0 equals V over R plus A, and e to the power 0 is 1. So this gives us A equals minus V over R. So we put all of this in, equals V over R, 1 minus e to the minus RT over L. Now, the question didn't say this, but let's plot this so we can kind of look what it does. This is T and this is the current. So we see at large times, this e to the minus RT over L, as T goes to infinity, this term here becomes very, very small. So it does essentially nothing. So at very large times, the current is just V over R, which is exactly what it would be without the inductor. It would just be V over R. So this means at large times, when the current is steady, the inductor's doing nothing. Also, we know that at low time, time is 0, the current was 0. So think, normally, if there wasn't for the inductor, you'd flip the switch closed and the current would run instantly, or pretty much instantly. But that happened. So when the current would normally be running instantly, the inductance is really high to cancel it out. Sorry, not the inductance. The voltage created by the inductor is really high to cancel out that current. And then the current varies gradually along the way. And we see that, say, here, the current is increasing quite quickly at the early times. And so the voltage created by the inductor is quite high, which means the current, which means it nearly completely cancels with the voltage from the battery. And so the current overall is quite low. Over time, the current becomes steadier. So as we see here, the current isn't changing very much. It's much shallower. This means the voltage created by the inductor is lower, which means it cancels less with the battery. And so the overall current through the circuit can be greater. So this is what I was saying earlier about how an inductor opposes a change in current. And the current's massively changing. It creates a voltage so that there's no current at all. When the current is steady, the inductor does nothing. All right. Does that make sense? Are we happy for me to go on to the last question? Okay. Let's move on to the last question. which is very similar to one that's in your sheet. So we have a solenoid of inductance L1, which is placed in an external magnetic field. We have a circuit. If I draw it, maybe I'll draw it. So we have one inductor. I'll draw a better spiral for you. That's not better. This is L1. This is L2. And the first inductor is placed in an external magnetic field, but the second one isn't. Now, this external magnetic field is just instantly switched off, or switched off extremely quickly. We're never told. Now, what's going to happen here? Well, an inductor is just a coil of wire, or usually just a coil of wire. Got a magnetic field through it, there's a flux. So while the magnetic field is constant, nothing happens. The magnetic field is instantly switched off, or quickly turned off. Well, this changes the flux through that inductor, and that causes, so the change of that flux creates a voltage, and that voltage creates a current around the wire. But as we create a current through the wire, well, there's two inductors in this circuit. So as the current tries to change, these inductors create voltages to oppose it. So there's quite a lot going on here. There's no resistors. So surely the current might be infinite, but if the current was to become infinite, the inductors would create the current would be changing infinitely quickly, so the current to the inductors would create an infinite voltage. So, and then when I looked at this, it was kind of hard maybe to get my head around. Maybe you think everything's going to be infinite. How can you work this out? But it does work out. So let's start with Kirchhoff's law. Remember, the total voltage going around a loop is zero. So the total voltage, the total EMF, is we have, so EMF is rate of change of flux with time plus, well, there's a minus sign actually, remember. Let's go around this way. So the rate of change of flux with time minus L1 di by dt. Remember, the current changes. That, because of the inductor, creates a voltage. And in fact, I'm going to put a little external on this phi, because it's the flux caused by the external magnetic field. And then we have minus L2 di by dt. Notice they all have the same sign. Now that's fine. The reason that's fine is they all have the same sign. They're all going to have a negative voltage. How is that going to work? Well, if the flux decreases, then the rate of change of flux goes down and the minus side makes that positive. Alternatively, it could be that we've picked a direction for the current and we find an answer where the current's going the other way. So whether it's all negative doesn't matter. That's just a directional thing. The other thing I want to say, and hopefully this doesn't make it more confusing. So we've got a flux created by the external magnetic field. But the inductor is a coil of wire, which, because of the current, creates its own magnetic field, which creates its own flux. So the reason I've done this is I've separated the two. The flux are, the flux from the external magnetic field and the flux created by the circuit itself, they can be treated separately. And this is the principle of superposition. You would have done the same thing when you work out, say, the Coulomb force from two charges. You just add the field from each charge individually. So we can treat each source of magnetic field separately, the external source and the source from the circuit. We can treat them separately. Maybe that made it more confusing. Maybe you were fine without that explanation. So let's have a look. And from Kirchhoff's law, this equals 0. So let's have a look. We have di by dt L1 plus L2 equals minus d phi by dt. Okay, I've just rearranged that. And now, if we multiply both sides by dt, we have di L1 plus L2 was minus d phi. Now, what is d phi equal to? Or rather, what is phi equal to? And then we'll look at the change. So let's start off with phi equals, there's a flux which is the magnetic field times area. But in reality, an inductor is a coil of wire. So the area is not just the area of one loop, there's going to be lots of them. So it's A times N, where N is the number of loops. You will have seen, I think, at least in the sheet, the notes you've been given, you talk about inductance and fluxes of solenoids. So this is just from there. But maybe it doesn't matter for the answer. So let's integrate this, or rather, we don't need to integrate it. Let's do this another way. So the total change in current, and the little d, it just means a small change. Everything here, because there's a change on both sides, it doesn't actually matter if it's small. Equals minus change in flux. So what is the change in current? Well, the change in current is equal to I take away 0, because the initial current is 0. We can take it to be 0. And what is the change in flux? Well, the final flux is 0 because the magnetic field is switched off. The initial flux is BAN. So we deal with these brackets and these zeros. We have I1 plus L2 equals BAN. I therefore equals B N, which is the initial flux, divided by L1 plus L2. Are there any questions? This is kind of odd. And in fact, what we find is, because inductors oppose a changing current, and there's no resistances to reduce the current, what happens is we just have inductors, the magnetic field switches off, and a steady current gets created over time. Are there any questions? Okay. Well, if there aren't any questions, I think if there aren't any questions, we can end the session and have a lovely weekend. And hopefully the sheet makes a bit more sense now. Glad you enjoyed it.